Examples of isomorphisms. First example, let G be an infinite group cyclic group. Then G is isomorphic to Z, because we know that Z is an infinite cyclic group. As G is a cyclic group, then A belongs to G will be your generator. This is a generator of G. Therefore, whole group G will be generated by generator A. Now define phi mapping from Z to G by phi k is equals to A to the power k. I am taking an element from Z, so k is an integer and it is mapped to G, and G is a generator A. So A to the power k type element will be there in this codomain for all k belongs to integers. Then phi is an isomorphism. Because it will be a group homomorphism also, 1 1 also, and onto also. Second example, let G be a finite cyclic group of order n. Then G is isomorphic to Zn. Here also let A belongs to G be the generator of G. Then as A is a generator of G and G is a finite cyclic group of order n, so order of A will be n only. Define phi mapping from Zn to G by phi m is equals to A to the power m for all m belongs to Zn. Then phi is an isomorphism. This means that if you have a infinite cyclic group, then it will be isomorphic to the set of integers Z, and if you have a finite cyclic group of order n, then it will be isomorphic to Zn. Note, two groups G and G bar are isomorphic if there exists at least one map phi mapping from G to G bar such that phi is bijective, means 1 1 and onto. Second, phi is operation preserving, means homomorphism. Second, if group G is not isomorphic to group G bar, then there does not exist any map between G and G bar which is an isomorphism. Third example, set of real numbers is isomorphic to set of positive real numbers under multiplication. So can you tell me which will be the map for this one? Because codomain is R plus set of positive real numbers.
X square.
X square.
Any map like G square of the elements. पॉजिटिव लेना है ना, तो पॉजिटिव अंडर मल्टीप्लिकेशन.
हाँ तो
इसका सॉरी मैं फंक्शन से रिलेट होकर गई, सॉरी फंक्शन से रिलेट कर गई.
मतलब
यहाँ पर
मैंने बस
हमारे
ये पूछा कि ऐसा फंक्शन जिसकी कोडोमेन पॉजिटिव रियल नंबर्स हो जो कि ग्रेटर देन 0 रहे, इक्वल टू 0 या लेस देन 0 ना होता हो, ऐसा कौन सा फंक्शन है? एक्सपोनेंशियल.
हाँ, यस, एक्सपोनेंशियल.
e to the power x for all x belongs to real numbers. So if I check 1 1, let x comma y belongs to real numbers such that phi x is equals to phi y. This implies e to the power x is equals to e to the power y. This implies e to the power x minus e to the power y is equals to 0. This can be also written as equal to 0 नहीं, e to the power 0. इसको भी अगर e to the power x minus y equal to e to the power 0. So x minus y is equals to 0. So x is equals to y. So phi is 1 1. For onto, for an element in codomain such that y is greater than 0, phi x is equals to y implies e to the power x is equals to y. Now taking natural log on both sides, x is equals to log y, x is equals to ln y. This belongs to real numbers. So phi is onto. Next, for operation preserving, let x comma y belongs to real numbers. Consider phi x plus y. I am writing it again. Here operations will be like this. Real numbers with respect to addition and r plus with respect to multiplication. So phi x plus y is equals to e to the power x plus y by definition of phi. This can be written as e to the power x into e to the power y. So phi x into phi y. So phi is operation preserving. Thus phi is an isomorphism, that is Real numbers with respect to plus operation is isomorphic to R plus with respect to multiplication operation. Fourth example, U10 is isomorphic to U5. Now here I don't have any map, so I cannot check 1 1 onto and operation preserving. So do you have any idea how to show that this is an isomorphism?
सेम 1 1 एंड और 2 शो करके
नहीं, 1 1 ऑन टू शो करने के लिए तो हमारे पास कोई मैप डिफाइंड होना चाहिए इसमें, अदरवाइज तो नहीं कर पाएंगे.
हाँ, इसके पहले एलिमेंट्स कितने पड़ेंगे फिर भी.
एक बार मैं पॉसिबल स्ट्रक्चर्स बता देती हूँ कि कैसे कैसे हम चेक कर सकते हैं. पॉसिबल स्ट्रक्चर प्रॉपर्टीज टू चेक आइसोमॉर्फिज्म. First, the group is cyclic. We can check U10 and U5 are cyclic or not. Second, the group is abelian. Third, the group has a specific order. Say 8. Fourth, the group is finite. And fifth, the group has exactly 2 elements of order 6. Means exactly 2 elements of a particular order can be there. So U10 and U5. What will be the elements of U10?
1 2.
U10 क्या था, बताया था मैंने.
The numbers less than or relatively prime to 10.
हाँ, so 1 3 2 नहीं आ सकता ना.
अच्छा, प्राइम करना था, सॉरी. हाँ ठीक है. 1 3 7 and 9.
Yes. And U5?
That is 1 2 3 4.
So clearly both have same order. Now let us check the element. Check the order of every element. So order of 1 is 1 only. Order of 3 is 3 to the power 1. 3 square is 9. 3 cube is 27. Modulo 10 will be 7 only. 3 to the power 4. 3 into 7 21 and modulo 10 will be 1. So order of 3 is 4. Is this clear? ये क्लियर हुआ कैसे निकालते हैं ऑर्डर?
यस मैम, पर मॉडल ही लेना है इसमें हमेशा में.
हाँ, इसमें मॉडलो ऑपरेशन बताया था मैंने साथ में. मॉडलो 10 होगा.
ठीक. और नेक्स्ट वाले मॉडल 5
क्या?
U5 में मॉडल 5.
हाँ, इसमें मॉडलो 5. मल्टीप्लिकेशन मॉडलो n होता है ऑपरेशन. सो ऑर्डर ऑफ 7.
सेवन का तो 7 है. 7 स्क्वायर का फिर 9 हो जाएगा.
हम्म,
है ना, और
7 क्यूब करोगे तो 7
तो
इंटू 9 63
343 डिवाइड बाय 9, 9 27,
नहीं, ऐसे
7
ऐसे मत करा करो, एक मिनट मेरी बात सुनो। 7 टू द पावर 1, 7 स्क्वायर इज 49, मल्टीप्लिकेशन मॉडलो 10 करके 9। अब जब 7
9
क्यूब करोगे ना तो बस 7 इंटू 9 कर दो, जो पिछले वाला नंबर आया था।
ओके,
7 क्यूब पूरा मत करो, बहुत बड़ा हो जाएगा कैलकुलेट करना।
तो 63 यानी 3 हो जाएगा फिर ये।
यस, 7 टू द
ठीक,
पावर 4, 7 इंटू 3 21, मल्टीप्लिकेशन मॉडलो 10 1। अदरवाइज कैलकुलेशन बहुत लेंदी हो जाएगी, आंसर तो सेम ही आना है।
ठीक है, ठीक।
एंड ऑर्डर ऑफ 9 विल बी
9
9 कैसे, 9 का ऑर्डर?
मल्टीप्लाई 10 से है ना।
हाँ,
अच्छा, वन, सॉरी,
पावर
वन
करते
वन,
जाओ, क्या होगा?
और मॉडलो 10 कर रहे हैं ना हम लोग, तो 9 नहीं आएगा रिमाइंडर।
मैं तो सीधा ऑर्डर पूछ रही थी, अभी आपने इतना ही करा। 9 टू द पावर 1 9,
अच्छा,
9 स्क्वायर 81,
1,
मल्टीप्लिकेशन मॉडलो 10 1, सो 2 हो गया ना।
हाँ,
So order of 1 in U5 is 1, order of 2 in U5 will be
तो 2 का स्क्वायर 4,
then 2 cube 8, 3 बचेगा, 2 to the power 4 6, 1 आ जाएगा 4, order of 3, 3 to the power 1 3, 3 square is 9, multiplication model of 5 4, 3 cube 12, 2 हो जाएगा, 3 to the power 4 फिर 1, so order of 3 is 1, sorry 4, and order of 4, 4 to the power 1 4, 4 square is 16, multiplication modulo 5 will be 1, so order of 4 is 2. So clearly U10 and U5 have 2 elements of order 4 and 1 element of order 2, and also it is cyclic because U10 has 2 generators 3 and 7, because they have same order as the order of group. So these are its generators, means U10 is cyclic also. Similarly, generators of U5 will be 2 and 3. U5 is also cyclic. Now I can use that result. If G is a finite cyclic group of order n, then it is isomorphic to Zn, and order is 4 here. So U10 is isomorphic to Z4 and U5 is isomorphic to Z4. And we know that isomorphism is an equivalence relation. So by transitive property, I can say that U10 is isomorphic to Z4 and it is isomorphic to U5. एक और बात यहाँ पे ऑब्जर्व करना कि अगर मैं लिखूँ U5 is isomorphic to Z4 या फिर Z4 is isomorphic to U5, दोनों बातें पॉसिबल है लिखना, दोनों बातें करेक्ट है. This implies that U10 is isomorphic to U5. Is this clear?
yes ma'am.
Okay. Next note. मतलब कोई भी क्वेश्चन आ जाए ना तो ये जो मैंने प्रॉपर्टीज लिखवाई हैं इनको चेक करना, क्योंकि हर बार ज़रूरी नहीं है कि मैपिंग डिफाइन करके हम चेक कर पाएंगे. ठीक है,
राइट.
आइसोमॉर्फिज्म
करोगे, मुझे थोड़ा लिखना है ऊपर से, थोड़ा सा लिखना है. पहले मैं समझ रही थी, थोड़ा नीचे नहीं, थोड़ा ऊपर, सॉरी ऊपर, ये तो हो गया, और थोड़ा ऊपर, लास्ट की 2-3 लाइंस बस बस.
कोई भी ग्रुप उठा के ना मतलब छोटा सा कोई भी ग्रुप उठा के Z5 उठा लिया, U5 या कुछ भी उठा लिया, उनके ना एलिमेंट्स के ऑर्डर निकाल के खुद से प्रैक्टिस करना, ताकि ऑर्डर निकालना आ जाए और स्पीड से निकालना आ जाए, ताकि फिर रॉन्ग ना हो.
Okay, ma'am, done.
So next note is this only: isomorphism is an equivalence relation. First is reflexive, means G is isomorphic to G. It can be easily shown by identity map. G is mapped to G. Ix is equals to X for all X belongs to G is an isomorphism. Second, symmetric. If G1 is isomorphic to G2, this means that there exists a map phi from G1 to G2 such that phi is an isomorphism. Phi inverse, it will be mapped from G2 to G1, and we know that inverse map is only possible when the map is bijective. So as phi is an isomorphism, so it is both 1 1 and on 2. That's why I am able to write this inverse. This is an isomorphism. This implies G2 is isomorphic to G1. Next, transitive. Let G1 be isomorphic to G2 and G2 be isomorphic to G3. This means there exists a map phi 1 mapping from G1 to G2 such that phi 1 is an isomorphism and there exists phi 2 mapping from G2 to G3 such that phi 2 is an isomorphism. So here I can apply composition. So phi 2 composition with phi 1 means firstly I will apply phi 1 G1 to G2, then phi 2 G2 to G3. So in this case G1 will be mapped to G3. This is an isomorphism. This implies G1 is isomorphic to G3. Now some questions on the topic which we have discussed yesterday, day before yesterday. How many homomorphisms F mapping from Z10 to Z25 are there? If F is a mapping from Z10 to Z2 cross Z3, how many homomorphisms are there? Let F be a mapping from Z2 cross Z4 to Z8 cross Z16. Calculate the number of homomorphisms.
फर्स्ट केस में तो 5 आएगा.
Yes. Simply GCD of 10 and 25, which is 5.
सेकंड केस में 1 आएगा.
1 कैसे, इसका कैसे होगा? GCD of 10 and 2 into GCD of 10 and 3.
अच्छा फिर 2 होगा.
Yes. And here GCD of 2 and 8 into GCD of 2 and 16 into GCD of 4 and 8 into GCD of 4 and 16. So it will be 2 into 2 into 4 into 4, 64.
64 है.
Yes. Next, the isomorphism theorems. These are important. And before that, I will discuss external direct product, which will be used in various questions. एक second. फिर से सेम इशू हो गया पेन टैब वाला. 1 मिनट में ट्राई कर रही हूँ. External direct product. Let G1, G2, so on till Gn be a finite collection of groups the external direct product of G1, G2, so on till Gn, which is denoted by G1 direct product G2, so on till Gn. This is equal to, this is basically in the form of a tuple, n tuple, G1, G2, so on till Gn, where this Gi belongs to group Gi for all 1 less than equal to I less than equal to n. First thing, external direct product of groups is again a group under the operation defined as G1, G2, so on till Gn, H1, H2, so on till Hn. This is equal to G1, H1, G2, H2, so on till Gn, Hn, where Gi, Hi is performed with the operation of group Gi. Whatever operation will be given in this group, we will apply that. Now some examples. First, Z2 direct sum Z3. So we know that elements of Z2 are 0 and 1. Elements of Z3 are 0, 1, 2. So it will be 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. So there will be total 6 elements. So order of this group will be 6. Second, Z5 direct sum Z2. So Z5 is 0, 1, 2, 3. 0, 1, 2, 3, 4. And Z2 is 0 and 1. So this will be 0, 0, 0, 1, 1, 0, 1, 1, 2, 0, 2, 1, 3, 0, 3, 1, 4, 0, 4, 1. So there are total 10 elements. So order of this group will be 10. Third, U5 direct sum with U3. So elements of U5 are 1, 2, 3, 4. Elements of U3 are 1 and 2. So this will be 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, 3, 2, 4, 1, 4, 2. So order of this group is 8. Next, Z direct sum with Z. This will be x, y such that x and y belongs to integers. Next, properties of external direct product. First property, order of an element of an external direct product of a finite number of finite groups, say is given by order of A comma B. Means I am taking one element from G1 and other element from G2. Then this ordered pair A comma B, its order will be calculated by LCM of order of A comma order of B. Second, let G and H be finite cyclic groups then G direct sum with H is cyclic if and only if order of G and order of H is relatively prime. Caution: the property 2 if we drop the finiteness condition, then even if G and H are cyclic, G direct sum H need not be cyclic. So counter example for this, let G equal to H equal to set of integers. We know that set of integers is cyclic. Claim Z direct sum Z is not cyclic. If possible, suppose that Z direct sum Z is cyclic. So if it is cyclic, then it will be generated by some element. So we are taking its generators as ordered pair A comma B. If A is not equal to B, then the elements of the type M comma N cannot be generated by A comma B, and if A is equal to B, then the elements of the type N comma M, where N is not equal to M, cannot be generated by ordered pair A comma B. Which is a contradiction, because we have discussed here that this is cyclic, so it is generated by this generator A comma B. And if it is a generator, then it will generate all the elements of this group. So we are getting contradiction, which is a contradiction. Therefore, our supposition is wrong. So Z direct sum with Z has no generators. Means this is not cyclic. Now some observations. First, Z2 direct sum with Z3. This was 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. Now I want to find element of every element, sorry, order of every element. So order of 0 comma 0. So this was LCM of order of 0 in Z2 and order of 0 in Z3. Order of 0 in Z2 is 1.
Yes.
Okay, so LCM of 1 comma 1, 1. Order of 0 comma 1. LCM of order of 0 comma order of 1. So LCM of 1 comma order of 1 in Z3 is 3. Is this clear? How it is 3?
Yes. Yes.
ठीक है. तो
ये
LCM
एडिशन मॉड्यूल लिया है ना हमने.
हाँ, ये एडिशन के रिस्पेक्ट में तभी हो रहा है ना कि अगर 1 का ऑर्डर निकालना है Z3 के अंदर तो 1 + 1 + 1 तब जाके 3 आएगा. फिर मॉडलो 3 करेंगे, एडिशन मॉडलो 3 तो 0.
पेंडो 0 है.
ऑर्डर ऑफ 0 comma 2 करना कैलकुलेट. ऑर्डर ऑफ 1 comma 0, ऑर्डर ऑफ 1 comma 1, ऑर्डर ऑफ 1 comma 2.
फर्स्ट इज 2 and 1. 2 आएगा एलसीएम.
0 comma 2 का
हाँ.
नहीं, इस 0 का एलसीएम तो 1 हो गया.
अच्छा 3 है ना. ठीक है, ठीक है, तो इसमें 3 आएगा फिर. 3. नेक्स्ट इज अगेन
नेक्स्ट तो
1. ठीक है. 3 6 2. ये इसमें 1. अच्छा 1 का 2 है. हाँ ठीक है, 2 है. 2 1 या 2 हो जाएगा. ठीक है. नेक्स्ट में ये हो जाएगा 1 2 या 2 and 3. 2 and 3 6 होगा. और इसमें अगेन 2 and 3
6. And order of Z2 direct sum with Z3 is order of Z2 into order of Z3. 2 into 3. 6.
yes.
So order of this group is 6. So can you tell me what will be the generators of this group?
Just 3. अगर इसका सेम होगा ना दोनों का, वो लेंगे ना फिर हम. 6 के लिए यही हो गया ना फिर. 1 1 और 1 2.
Yes. As Z2 direct sum Z3 has generators 1 comma 1 and 1 comma 2. So this is cyclic. ठीक है, ऐसे भी देख लिया. एक और तरीका है साइक्लिक देखने का. इफ Zm direct sum Zn, this is cyclic if and only if GCD of m and n is 1. Means if they are relatively prime, then it is cyclic. Here 2 and 3, their GCD is 1, they are relatively prime, so that's why it is cyclic. Note, if G and H are finite groups, then order of G direct sum with H is equals to order of G into order of H. So there exists A comma B belongs to Z2 direct sum Z3 such that order of A comma B is 6. And this ordered pair was 1 comma 1 and 1 comma 2. Z2 direct sum with Z3 is cyclic, and we have already discussed that if G is a finite cyclic group of order n, then it is isomorphic to Zn. So here Z2 direct sum with Z3 will be isomorphic to Z6. Okay. मतलब पेपर में ऐसा हो सकता है कि कुछ ऑप्शंस दे दें और पूछें कि कौन सा किसके आइसोमॉर्फिक है, तो ये रिजल्ट्स अप्लाई करने आने चाहिए. ठीक है. नेक्स्ट एग्जांपल Z2 direct sum Z2. So it will be 0 comma 0, 0 comma 1, 1 comma 0, 1 comma 1. So order of 0 comma 0. Quickly find all the orders.
इसको हम डायरेक्टली कह सकते हैं साइक्लिक नहीं होगा क्योंकि इसका जो वो होगा जीसीडी वो 2 होगा.
डायरेक्टली भी कह सकते हैं. दोनों तरीके हैं हमारे पास, या तो हम एलिमेंट्स का ऑर्डर निकाल के कर ले या फिर जीसीडी दोनों का देख ले. So 1 2 order of 1 comma 1 this is 2, order of 1 comma 0 is 2. Clearly group has order 4 but there does not exist any element of order 4, means we do not have generator for this group. There does not exist any A comma B belongs to Z2 direct sum Z2 such that order of A comma B is 4. This implies Z2 direct sum Z2 is not isomorphic to Z4 because it was not cyclic. So we can apply that contrapositive here now. If G is a finite cyclic group of order n, then G is isomorphic to Zn, and its contrapositive will be G is not isomorphic to Zn implies G is not a cyclic group. Next, Zn1, N2, so until Nk. This is isomorphic to Zn1 direct sum Zn2 direct sum Znk if and only if GCD of Ni comma Nj is 1. For all I not equal to j, 1 less than equal to I, comma j less than equal to k. Means अगर कोई भी हमें दे रखा है तो उसको हम आइसोमॉर्फिक टू डायरेक्ट सम लिख पाएंगे कब, जब जीसीडी उनका 1 हो, अदरवाइज नहीं लिख सकते, जैसे यहाँ पे हम नहीं लिख पाए. Here n1 was 2 and n2 was also 2. Let us consider Z30. Now if I want to write the Z30, then I need to write it as those Ni and Nj whose GCD will be 1. So I can write it as Z2 direct sum with Z3 direct sum with Z5. Simply prime factorization of 30. Okay. Next, isomorphisms of unit groups. This is also important. First, U2. This is isomorphic to 0, which is equal to Z1. U4 is isomorphic to Z2. U2 to the power n. This is isomorphic to Z2. Direct sum with Z2 to the power n minus 2 for n greater than equal to 3. Because for n equal to 2, we have already shown this. And for n equal to 2 square, this is 2 square, na? That's why n greater than equal to 3. Fourth, if p is any odd prime, then u p to the power n is isomorphic to z p to the power n minus p to the power n minus 1. Example, consider U105. Now its prime factorization will be 3 into 5 into 7. So it will be isomorphic to U3 direct sum U5 direct sum U7. Now by using these results, can you tell me it will be isomorphic to
U5 is isomorphic to Z4.
U5 is isomorphic to Z4, ठीक है. U3
U3 is isomorphic to Z2.
yes.
And U7 is again isomorphic to 6.
Yes.
Z6.
Z6. G direct sum H is abelian if and only if G and H are abelian. Sixth, if G1 is isomorphic to G2, H1 is isomorphic to H2, then G1 direct sum H1 is isomorphic to G2 direct sum H2. Please mute yourself. G direct sum H is isomorphic to H direct sum G. 8th, A direct sum B is isomorphic to A direct sum C if and only if B is isomorphic to C provided A is finite. Next, we need to show that D33 is not isomorphic to D3 direct sum D11. Now, possible order of elements in D33 will be the divisors of 33. Divisors of 33, एक सेकेंड, इसका जो ऑर्डर होगा 2 into 33 66 होगा ना. So possible orders of D33 will be 1, 2, 3, 11 and 33. And possible orders of elements in D3 direction D11. D3 order will be 6, so possible divisors are 1, 2 and 3, and for one second it is Z11. For Z11 possible orders will be 1 and 11. So possible orders will be 1, 11, 2, 22, 3, 33. How I have written this? Is this clear? Simply LCM of 1 and 1, then LCM of 1 and 11, LCM of 2 and 1, LCM of 2 and 11, LCM of 3 and 1, LCM of 3 and 11. So D3 direct sum with Z11 has an element of order 22, but D33 does not have an element of order 22. So they are not isomorphic. Is this clear?
Yes, ma'am.
Next, the first isomorphism theorem. Let phi mapping from G to G bar be a group homomorphism then the map psi from G upon kernel phi to phi G means image of this group G defined as psi G kernel phi is equals to phi G is an isomorphism. This means that G upon kernel phi is isomorphic to phi G. Next, if phi mapping from G to G bar is any group homomorphism, then G by kernel phi is isomorphic to phi G. If phi is onto. Now if phi is onto, then codomain is equals to if phi is onto, then codomain is equals to range. So G by kernel phi will be isomorphic to G bar. Next, the second isomorphism theorem. Let G be a group and K be a subgroup of G and N. Be a normal subgroup of G, then K by K intersection N is isomorphic to Kn by N. Next is third isomorphism theorem. let M and N be normal subgroups of the group G such that N is a subgroup of M, then G by N upon M by N. This is isomorphic to G by M.